Today it's our fourth class. We're gonna talk a little bit about how you can use set theory for probability. We're just gonna talk about some ideas in probability in general. As usual, feel free to stop me along the way if you have any questions. First, we're gonna review a little bit of what we talked about last time. So remember, we talked about the Cartesian product. The Cartesian product of two sets is a set of all ordered pairs, A, B, where A is in set A and B is in set B. So it's all of the ordered pairs of numbers or elements from each set. And then the power set is the set of all subsets. So you'll remember that we used this P of A to represent power set. Today we're going to be talking about probability, which can also be written using P of A. So whenever I use P of something today, that'll mean the probability of that event. I'm not going to write power set that way today to avoid confusion. So just today, remember, P means probability. All right. So the definition of probability. So the probability of an event is the likelihood that that event will happen. Numerically, it is the number of favorable outcomes divided by the total number of outcomes. So if I flip a coin, the heads is one outcome and tails is the other outcome. So the probability of heads is 1 divided by 2 or 1/2, and the probability of tails is 1 divided by 2 or 1/2. So how can we use this in set theory, or how can we use set theory to represent this? We can consider the possible outcomes for an event using a set. So we'll have a set S that represents all of the possible outcomes, and this is called the sample space. The sample space for a coin flip would be HT or heads and tails. You could write it either way. But the point is that we have two outcomes and they are in a set, heads and tails. And then to calculate the probability, you take the set of successes and you divide the number of elements in that set by the number of elements in the sample space. So hopefully that makes sense. We'll do a few practice questions. So what is the sample space for a die roll? You can let me know with your voice or using the chat. What is the sample space for a die roll? So the set of outcomes that you could get when you roll a die. So some people have said 6, some people have said something else. So 6 is not right. So 6 is the number of outcomes you could get, but the sample space is going to be a set of possible outcomes. So it's going to be the set of numbers 1 through 6, which, if you remember how you write sets, it's going to look like, let me just write it. It's going to look like this. So that is the sample space for a die roll. That is the set of outcomes you could get when you roll a die. How about the second one? If I roll 2 dice and consider the pair of numbers that I roll, what is the sample space for this? So you can represent the pair of numbers you get with a ordered pair. And because we're rolling 2 dice, there's going to be a lot of possible outcomes. So there might be a shorter way to write it using a Cartesian product. So Andy says 1 through 36. So we're not looking at the product of the numbers or the number of ways of pairs we could roll. We're looking at what the pairs are themselves. So an example of a pair you could get is something like this. You could roll 1 and 1, you could roll 1 and 2, you might roll 5 and 6. So there's going to be a lot of these. But there's a shorter way you can write it using the Cartesian product. So see if you can figure that out. I want to see a couple more answers from people before I give the answer. So remember, the way we write a Cartesian product is we're going to have one set. So it's like set A, and then we're going to write, I don't have we're going to write it as set A times set B. And that's going to be the set of all elements, one from A and one from B. So if you can figure out how to use this idea to consider the number of, or consider the set of pairs you could roll when you're rolling dice. So remember, the sample space for the first die roll was this. And then we're going to have the same sample space for the second die roll. And if we want to do a Cartesian product, it's going to be all of the possibilities from the first one and then all of the possibilities from the second one. Hannah just wrote it correctly. So that's going to look like this. It's the Cartesian product of this set times this set. And that's going to be all the possible combinations of two numbers that we can roll. So these are the answers. Does anyone have any questions about these questions? All right, we'll move on. So we just did. This is what's up. Oh, okay. So we're gonna do some probability practice. Oh, so before we move on, Eli just sent me the complete answer that doesn't use the Cartesian product, and it's a little longer, but it's also correct. I'm just gonna copy it in so you can see it. So this is, I think it is. Looks like all of the possible combinations you can roll of two dice, or at least close to all of them. I don't want to count them, but that's another way you could write the answer. All right, now we'll do some practice with calculating probability. So right now we were just finding sample spaces. Now we're going to look at the actual probabilities of events happening. So first, the first question we're looking at, what is the probability of rolling an even number? So you might be able to just do this intuitively or find an easy way to calculate it. But what you can do first is find the subset of this sample space that represents rolling an even number, and then you can divide the size of that set by the size of the sample space, and you'll have the probability. Yeah, so Andy says that the sample space, or sorry, the set of even rolls is going to be 2, 4, and 6. And so that has 3 elements, and the sample space has 1, 2, 3, 4, 5, 6 elements. So 3 divided by 6 is 1/2. So the answer is 1/2. How about the second one? What is the probability of rolling a number less than 4 on one die roll? Yep, this one's not too hard. It just, you can have 1, 2, or 3. And that has 3 elements, and then the sample space has 6 elements, so it's going to be 1/2. Does anyone have any questions about these? Let me see how we're doing on time. So on the, okay, very good. Let's see. Now we're going to talk about what mutually exclusive events are. So events A and B are mutually exclusive if the probability of A intersection B is 0. So if you think about what that means, it means that we never have an intersection of A and B. So A and B never happen at the same time. So if you roll a die, rolling a number that is even and rolling a number that is odd are mutually exclusive events because one roll can only be either even or odd. So there's never a time when it's both even and odd. So those are two mutually exclusive events. Rolling an even number and rolling a number less than 4 are not mutually exclusive because a number can be less than 4 and be even. That would be 2. So 2 is less than 4 and it's even. So these are not two mutually exclusive events. Does that definition make sense to everyone? All right, we will do some practice with this. So if I flip a coin, are heads and tails mutually exclusive?
Number 1, yes.
Yep, they are mutually exclusive because you can never have both heads and tails. The second one, if I roll 2 dice, are rolling at least one even number and rolling at least one odd number mutually exclusive events? And if they are mutually exclusive, what is the subset of the sample space that represents the intersection of these two events? So start by checking if it's mutually exclusive. Oh, this shouldn't say if, so this should say if they are mutually exclusive. So if they're not mutually exclusive, what is the subset of the sample space that represents getting at least one even number and getting at least one odd number? That's going to be a little long. You can also, there might be a shorter way to write this one, but might be a shorter way to write this one, but yeah.
Well, the subset would basically be rolling an even number first and then an odd number, or an odd number first and then an even one.
Yeah. Don't think I actually wrote that part of the answer here, but you're exactly right. It would be all of the ordered pairs with an even number followed by an odd number, or all of the ordered pairs with an odd number followed by an even number. Any questions about this so far? All right. Then we will keep going. Now we're going to talk about independent events. So events A and B are independent if the probability of A times the probability of B is equal to the probability of A intersection B, which is the same as the probability of A and B happening together. So if two events are independent, it means that one event does not affect the probability of the other occurring. So if I flip a coin twice, getting heads on the first flip and getting heads on the second flip are independent events because they don't affect each other. If I get heads on the first flip, it doesn't change whether I get heads or tails on the second flip. So that's why they're independent. And if we look at the math behind it, so the probability of heads the first time is 1/2. The probability of heads the second time is 1/2. So that's 1/2 times 1/2, and that's 1/4, which is the same as the probability of getting heads and then heads, which is also 1/4. But we might have a situation where the probabilities individually multiplying do not equal the probability of them happening together. So, for example, Yeah, let's imagine that I have like a bag with a few marbles. I'm gonna draw them up here. So this is we have a couple of red marbles, and then we have a blue marble. Not the best drawings of marbles ever, but should be good enough. So if I pick a marble out and then pick another marble out, the first marble I pick is going to affect the probability of the color of the second marble I pick. So if I pick a red marble the first time, then there's a 50% chance that I get another red marble and a 50% chance I get a blue marble. But if I pick a blue marble the first time, there's a 100% chance that I'm going to get a red marble the second time. So that's a case where these two events would not be independent. The first one affects the second.
So those two. So the second event is dependent.
We don't usually say dependent, but you could say that. But I think the main way you would say it is that they are not independent. Yeah, it just means that the one event affects the probability of the other event happening. All right. So now we have some practice with independent events. So if I flip a coin, are getting heads and tails independent events in one flip. So I've seen a few people say yes. So think about, if I flip a coin once, if I get heads on that flip, does that affect the probability of whether I also got tails on that flip? It's kind of a hard thing to think about. But actually, these two events are not independent, because if I flip a coin and I get heads, that means that there's a 0% chance that I got tails. If I flip a coin and I get tails, that means there's a 0% chance that I got heads.
Can you also do like the formula?
Yeah, we can look at the formula.
Yeah, so there's a 0.5% chance to get head and 0.5% chance to get tails. And the intersection is 0?
Yeah, exactly. So the probability of heads times the probability of tails, right? These are our two events, equals, this is 1/2 times 1/2, and this is equal to 1/4. But the probability of getting heads and tails at the same time, right? It's only one flip, so we can't do that. So that has a probability of 0, and 1/4 is not 0. So these two events are not independent, right? Remember, going back to our formula, let's see. Just want to go. They have to be, if they're independent, the product of the probability separately has to be the same as the probability of their intersection. But here you can see that those are two different values. So that's the mathematical way to think about that one. All right, let's do the second one. If I do 2 coin flips, are getting heads the first time and getting tails the second time independent events. So this time we're looking at 2 coin flips, and heads in the first one and tails in the second flip. Are those independent events? Yeah, so these are independent events because they don't affect each other's probabilities. So if I get heads or tails the first time, it doesn't determine whether I get heads or tails the second time. And mathematically, it's going to be the same formula. 1/2 times 1/2 the first time, or for the probability separately is 1/4, and then the probability of getting heads and then tails is also 1/4. So these are two independent events. In this last situation, we have one die roll, or rolling an even number and rolling a number less than 4 independent events. So rolling an even number on a die and rolling a number less than 4 on that same die are those independent events. Yeah, these are not independent events. And let's look at why. So the set of outcomes where it's, if we look at even separately and less than 4 separately, so even would be 2, 4, or 6. Less than 4 would be 1, 2, or 3. And then both would be only 2, right? So 2 is the only number less than 4 that is even. So if we look at multiplying the probability of even and less than 4 together, that's 1/2 times 1/2 equals 1/4. But if I look at the probability of their intersection, that's only 2, so that's only 1 out of 6. And 1/4 is not equal to 1/6. So these two events are not independent. Any questions about any of this? All right. There's solutions one more time for you guys to look at. All right. Oh yeah, and this is the other solution. All right. So now we can take advantage of the definition of independent events. So if we know two events are independent, we can use the definition and find the probability of two independent events happening at the same time by multiplying their separate probabilities. So for example, if I flip a coin twice, I know those two flips are independent. So instead of counting the number of ways that I get heads and then tails, and then dividing by the total number of cases, I can just multiply the probability of heads the first time by the probability of tails the second time. So instead of saying, you know, if you want to count them out, it would look like, well, we could get heads then tails, we could get tails then heads, we could get heads and heads, or we could get tails then tails, right? And so we could say heads and tails is this case, and that's 1 out of 4. So our probability is 1/4. Instead of doing that, we can just say the probability of heads the first time is 1/2. The probability of tails the second time is 1/2. So our probability of them happening together is 1/4. So we can use this whenever we have two independent events, and we will do some practice with that. All right, so if I roll a die 6 times, what is the probability of rolling a 5 6 times? What is the probability of rolling a 4 6 times? You don't have to calculate the exact answer on this one. You can just leave it as an expression, or you can use a calculator if you want. So rolling a die 6 times, what is the probability of rolling 6 5s in a row? And then what is the probability of rolling 4 6s in a row? Or sorry, 6 4s in a row? Shouldn't be too hard to figure out that second one once we get the first one. Yeah, so this is actually going to be 1/6 to the power of 6. And if you haven't heard of exponents before, that's just saying 1/6 times itself 6 times. Oh, that's good. 2, 3, 4, 5. Yeah, so these are independent events. Each die roll is independent of the last die roll. So we can multiply the probability of getting a 5 each time. So the first time it's 1/6, the second time it's 1/6, third time it's 1/6, and so on. And that is going to equal, Eli just said it, 1 over 46,656. All right. If there's no questions about that, we can move on to the second one. If I roll a die and I flip a coin, what is the probability of getting heads on the coin and 5 on the die? Double check your answer, Lily. One more answer from you before I give the answer. So remember, these are two independent events. You figure out the probability of them separately and then multiply those probabilities together. So the probability of rolling a 5 on a die is 1/6. The probability of getting a heads on a coin is 1/2. So we can multiply these together because these are independent events, and we will get 1/12. Any questions there? This is all we have left on the PowerPoint, so we're going to go to the Kahoot after this. So if you have any questions on anything so far from the whole time, now is the time to ask. All right. Cool. I will switch to sharing the Kahoot. We can get set up for that. See. So you guys can join. Give you about 5 minutes to get in, and then we'll get started. About 2 more minutes. Try to get in here if you would like to play. All right, we will get started now. We're going to start with a couple of review questions, and then we have a bunch more questions from today. We'll see. We should be able to finish most of them, hopefully with some time left over at the end. Well, this one was hard, it looks like. So remember, the Cartesian product is a set of all ordered pairs with one element from one set and the other element from the other set. All possible ordered pairs that way. So we're going to have A and B such that A is in A, in set A, I should say, and B is in set B. So remember, the power set is going to be a set of all subsets. The union is going to be all of the elements that are in both sets. So this is looking at two elements from different sets, and the union is going to be looking at elements in both sets, at least once. And then the intersection is going to be all of the elements that are in A and also in B. We can go to the next question. Let me know if there's still any confusion about the difference between all these terms. Remember, using our set builder notation, this is going to be read as the set of all X, such that X is a subset of A. Yes, you did better on this one. So Remember, the power set is a set of all subsets of A. So in our set builder notation, the set of all X such that X is a subset of A. That is going to be the power set. So if we have a sample space of the numbers 1 through 6, what is the subset of S that represents getting a number greater than 2?
I messed up on this one.
Well, hopefully you learn from your mistake. Yeah, so this one is going to be 3, 4, 5, and 6. Those are all the elements in the set that are greater than 2.
Because I clicked the wrong one.
Oh, well, that's okay. Hopefully you know it. And so again, if our sample space is numbers 1 through 6, this time what is the probability of getting a number greater than 2? Nice job. Everyone got this one. Yeah, so remember we have 3, 4, 5, or 6. So that's 4 elements out of a sample space of 6 elements. And 4 divided by 6 is 2/3.
That one was really easy.
Oh, I'm glad you got it right.
I can't. It just lagged on me.
Oh.
Wait, what's blue? Oh, never mind.
Yeah, so for this one, you need to remember what mutually exclusive means. Mutually exclusive means that they can't happen together, but here they can happen together. We could get a heads, and then a heads the second time. So they're not mutually exclusive. Then everyone said they're independent, which is good because they are independent. Getting a heads the first time doesn't affect the probability of whether you'll get a heads the second time. So well done there. So if I roll a die, are getting a number less than 5 and getting an even number on that roll, are those two events mutually exclusive or independent? Looks like another hard one.
Hey,
So
I got this one right.
nice job. So they're not mutually exclusive because you can get a number that's less than 4 that is also an even number. So 4 and 2 both work. So they're not mutually exclusive. The hard thing is you have to figure out whether or not they're independent. So we had one that was kind of like this before where it was less than 4. And in that case, they were not independent. But in this case, if you actually look at it, the numbers that are even are 2, 4, and 6 out of the entire sample space. The numbers that are less than 5, I wonder if I messed this question up. Maybe I did. Looks like I messed this question up. So you guys might have been right, but we'll go through the math anyway. So in this case, you have a 2/3 times a 1/2 chance of getting both of them or multiplying them separately. That's going to be 1/3. Then if you look at the probability of getting a number that is both even and less than 5, that's going to be 2 and 4. Okay, looks like it didn't mess this up. And that's going to be 1/3. Yeah, so these two events are independent because the probability of multiplying them separately is the same as getting both events at the same time. So if a number is less than 5, that doesn't affect whether it's likely to be even or odd. If you get a number that's even, that doesn't affect the probability of whether it would be less than 4. So sometimes you do have to calculate out all the possibilities. So can two
Everything
mutually
froze.
exclusive, sorry?
Never mind.
Can two mutually exclusive events ever be independent?
Wait, what does mutually exclusive means again?
That means that they can never happen at the same time. So if you have two events that are mutually exclusive, that means they never happen at the same time. An example is getting heads on a coin flip and tails on a coin flip in the same flip. You can never have both heads and tails at the same time.
Oh, I messed up. I forgot. I didn't see the red one.
We will see what the answer is. So mutually exclusive events are not always independent. In the example of the coin flip, heads and tails in one flip are mutually exclusive, and they are not independent because if you get heads, that means you didn't get tails, and if you get tails, that means you didn't get heads. So those two events are not independent, but they are mutually exclusive. The only way you can get two mutually exclusive events also be independent is if one of the events has a probability of 0, meaning it never happens. So the probability of, or sorry, the rolling a 7 on a 6-sided die and rolling a 3 on a 6-sided die are mutually exclusive events, and they are also independent because the probability of getting a 7 is always 0. So if you roll a 3, that will not change the probability of whether you can roll a 7. Hopefully that makes some sense. Well done. Most of you got this one. Yep, so this one is just the number of elements in A is 5, 7, and 9, so that's 3. And then the number of elements in the sample space is 6. And 3 divided by 6 is 1/2. So that is the probability of A. So write the sample space of 2 coin flips as a Cartesian product. So remember, the Cartesian product is going to take the ordered pairs with one element from the first set and one element from the second set. Yeah, so this is going to be the red answer. The number of, or the set of outcomes for the first coin flip, it's heads and then tails. And that's also the set of outcomes for the second coin flip. And if we take the Cartesian product of those two sets, that will give you all the possible ways to get one flip and then another flip. So if you flip a coin, what is the probability that you'll get neither heads nor tails on that flip?
Okay, what would infinity be an answer?
I don't know. Yeah, so it is 0. There's never going to be a situation where you get neither heads nor tails on a normal mathematical fair coin. Some people might say that you could have the coin land on its side, but when we're doing math, we don't like to worry about that situation.
Three-sided coins are weird.
Yeah. Paul asked a question about infinity, and you could actually never have a probability be infinity because we always say that probability is between 0 and 1. So that's just kind of a trick answer that you would never have. So if you flip a coin, we have 2 events. One of the events is getting neither heads or tails, then the other event is getting heads. Are these 2 events independent? So does one affect the other? So these are 2 independent events. Because you'll never get neither heads nor tails, that is always going to happen, and so it's never going to affect the probability of getting heads. The probability of getting heads is always going to be 1/2 in this case. So now we're looking at the same set of events, and we're asking if they're mutually exclusive.
It means that can never happen, mutually exclusive.
Mutually exclusive means that they never happen at the same time. Yeah, so because we'll never get neither heads nor tails in the first place, this event will be mutually exclusive with every event because this event can never happen at the same time as another event. So they are mutually exclusive. This is our last one. If I rolled 2 dice, what is the probability of getting 2 heads on the coins and 2 5s on the dice? Well, I'm not sure I said that right, so I'll say it one more time. If you flip 2 coins and roll 2 dice, what is the probability of getting 2 heads on the coins and 2 5s on the dice?
I'm not sure about this one.
So remember, you can use the fact that they're independent events and multiply the probabilities together of each event separately. Yeah, so this one's going to be 1 over 144. We can look at the math for this. So the probability of getting 1 heads is 1/2, and then we can multiply by 1/2 again for the second heads. Then the probability of getting 1 5 is 1/6. The probability of another 5 is times 1/6. So it's going to be 1/2 times 1/2 times 1/6 times 1/6, and that's going to be 1 over 144. And that is all we have today. If you have any questions, you are free to ask me.